Imagine a cosmic lighthouse shining its beam across billions of light years. That's a blazar, one of the most energetic and fascinating objects in the universe. Blazars are active galactic nuclei, or AGN, which are incredibly luminous centers of galaxies powered by supermassive black holes. But blazars are not just any AGN, they are the extreme athletes of the cosmos, blasting out jets of particles at nearly the speed of light. These jets are so powerful that they outshine the combined light of billions of stars in their host galaxy. It's like a single spotlight shining brighter than an entire city. This makes blazars visible across vast cosmic distances, allowing us to study these enigmatic objects and the processes that drive them. Their extreme nature provides valuable insights into the physics of black holes, particle acceleration, and the evolution of galaxies. By studying blazars, we can peer into the hearts of distant galaxies and unravel the mysteries of the early universe. At the heart of every blazar lies a supermassive black hole, a region of space-time where gravity is so strong that nothing, not even light, can escape. These cosmic monsters can be millions or even billions of times more massive than our Sun. As matter falls toward the black hole, it forms a swirling disk of gas and dust called an accretion disk. This material doesn't fall directly into the black hole. Instead, it spirals inward like water going down a drain. As the material gets closer to the black hole, it heats up due to friction and gravitational forces. This superheated material emits intense radiation across the electromagnetic spectrum, from radio waves to gamma rays. However, not all of the infalling matter ends up in the black hole. Some of it gets channeled away from the accretion disk and ejected outward in the form of powerful jets. These jets are launched from the poles of the black hole, perpendicular to the accretion disk. The exact mechanism behind jet formation is still not fully understood, but it is thought to involve complex interactions between the black hole's spin, magnetic fields, and the surrounding material. Imagine a fire hose connected to a fire hydrant. When the hydrant is opened, water bursts out with tremendous force, creating a jet of water that can travel a considerable distance. Blazar jets are similar, but instead of water, they are made up of charged particles, mainly electrons and positrons, accelerated to nearly the speed of light. These particles are propelled by powerful magnetic fields that thread through the accretion disk and the black hole itself. As these particles spiral along the magnetic field lines, they emit radiation, primarily in the form of radio waves, visible light, X-rays, and gamma rays. This process is called synchrotron radiation. The jets emitted by blazars can extend for millions of light years, stretching far beyond the confines of their host galaxies. These jets are not just a visual spectacle, they are also incredibly powerful, carrying away vast amounts of energy from the black hole and its surroundings. Imagine pointing a flashlight directly at someone. The light appears brightest when the flashlight is pointed straight at the observer. Blazars work in a similar way. What makes blazars stand out from other active galactic nuclei is the orientation of their jets. In most AGN, the jets are oriented at random angles relative to our line of sight. However, in blazars, the jets are pointed almost directly at Earth. This alignment is purely by chance, but it has a dramatic effect on how we observe these objects. Because the jet is pointing towards us, the radiation we receive is beamed and amplified, making blazars appear much brighter than they would if their jets were oriented differently. This beaming effect also makes blazars appear to vary in brightness much more rapidly than other AGN. Astronomers classify blazars into two main types based on their spectral characteristics, or the specific wavelengths of light they emit. BL Lacertae objects, or BL lacs, and flat-spectrum radio quasars, or FSRQs. Both types share the same basic properties of blazars, but they differ in some key aspects. BL lacs are characterized by their relatively weak emission lines, meaning they show fewer distinct spikes in their spectra. They are also highly variable in brightness and tend to be found in elliptical galaxies. FSRQs, on the other hand, exhibit strong emission lines in their spectra, indicating the presence of a more prominent accretion disk and a denser surrounding environment. These differences suggest that BL lacs and FSRQs may represent different stages in the evolution of blazars, or that they are powered by black holes with different masses and accretion rates. However, more research is needed to fully understand the relationship between these two blazar subtypes.
Like and subscribe to start your journey today.